Non riesco aspetta, non c'è più. Sì, no, invece non sì, sì.
So I decided that we will not finish the class on autoencoders because it's more important that we advance the other topics. You have the slides, so I mean you can look a bit at what I was going to tell last week, but it's not so urgent, I'd say. So I mean, so okay. Okay, put this in silent now. This is a bit disturbing. Okay, so today we will talk about attention, which is without any doubt one of the most important concepts that has been developed in deep learning in the last 10 years. And we will have three sections today. First is to explain the idea of attention. What do we want to do there actually? Then we will see that attention has kind of sub-function. So it's like you can parameterize attention with a function, and then we will see different functions that you can use there. And finally, we'll talk about the famous self-attention, multi-attention mechanisms that were introduced by Vaswani in 2017 in this transformer paper. But we will not talk about transformers today, okay? So that will come later. So a transformer is not simply a neural network with an attention mechanism. Okay, so the problem we want to solve is that one that we already addressed before. Okay, so it's not a new problem. It's only that we have a new way of solving. Okay, so what we want to have is contextual embeddings. Yeah? So we've talked about that before with this bank example. So I could say maybe I encode the word bank in a vector, but bank can have different meanings depending on the context, right? So depending on the context, we want maybe different representations of the same word, okay? And the idea will be, wouldn't it be great if we could, let's say, well, I mean, what is context? Context is I have a word bank and I have another word that poses a bit the situation. So here it would be river. And now it would be great if this contextualized representation of bank would be a kind of linear combination of this vector and this vector. Because we can contextualize the vector of bank in whichever way we want. Okay? Nobody would stop us from doing that. But it would be convenient if we would have this kind of additivity thing. Bank in the context of river is representation of bank plus representation of river, or let's say and put some weight on each of the two vectors, okay? That is a bit related to this composability property that you say the representation of king minus man plus woman is the embedding of queen, okay? A bit related, okay? Why would that be very convenient? Well, because then we could try to find, okay, so if we had that, then we could just say, okay, so we have several items in a structure, each of them has an embedding, and we like compare them, and we see, bank occurs in the context of river, so we, let's say, correct bank to the bank in the river context. Yeah? So that would look like this, maybe. So the red one is the context tree bank. And if my children told me that if you mix red and blue, you get purple. So that's why it has this color. Now, And what about the other bank with the account? Okay, so maybe we have an account, and if then the bank occurs in the context with the word account, then we want some other context embedded. Okay, and that would give us maybe then a vector here. Because yellow plus red is orange. As you can see here, the bank is really in the middle of the two. Here it's not in the middle, it's like closer to account. We'll talk about this later. So I'm not saying here that it's always going to be in the middle. And actually, it will be even the product of not only two vectors, but of more vectors. But in general, that should be the idea. Okay, let's say we correct or adjust the representation somehow based on the context. That should be the idea. Okay, and today we will do nothing else except an understanding how this can be done or automatized. Okay. So one important problem maybe here, issue that we should solve is if we want to do this, we should make sure somehow that between these things that we want to combine, there is enough space. Because if they are super close to each other, then maybe it's difficult to differentiate these two things. Okay, so if river would like already be down here, then the point in between would be, yeah, there's not a lot of space where I could put this other bank, okay, this contextualized bank. So it's good if we have here a lot of space, so I can really very well distinguish this river from this bank by the river, okay? So that would be somehow important, create enough space where we can then move these additive operations. Good, okay. So now let's put this into a bit more formal context. Yeah. So let's say now that we have an encoding V of n objects in dB dimensions. Okay, so B is a matrix. Every row is for one object, maybe a word. Okay. And dB is the dimensionality of this representation. So in the example we just had, we have three words. We had three words. We had bank, river, and account. Yeah. So n would be 3. And dB, what was dB? The dimensionality, and that was 2. Because I have a plane, okay? An Euclidean plane. So in this case, my vocabulary is explained in vectors of 2 dimensions. So that I could describe this figure without the mixtures, and just the 3 pure words, bank, river, and account, in a 3x2 matrix. Yeah. Okay. So, and where do these embeddings come from? Well, it doesn't matter at this point, but could be we trained a word to vec embedding, for example, as we did on the second sheet. Yeah. So somehow we did that. And now we come. Okay, and now we have 3 like objectives. So first thing is what we want to do is that we have a new object Q in a different space. Okay, so Q is a vector from the space R to the dk. It's not the same dimensionality. Yeah, it could be the same for coincidence, but not necessarily it will be the same. So it could be that dk is just 1. So Q would be just a number 5. Okay. Okay, so that would be now another word that we want to replace. And so we want to somehow encode this here, this Q, in terms of this vocabulary up here. Okay, and what we want is that the encoding, this is what I meant by this composability, we want that somehow this new representation is a linear combination of these words up here. Yeah. Is this I want maybe that bank would be bank, the combination of bank and river, yeah, or bank or account. And what are the weights in this linear combination? Well, they should be somehow governed by the relevance. Okay, so every word or every object here in my catalog has something to do with this query. Yeah, some words have more to do with memory, others have less to do. And I want that, depending on how important they are, they should get a bigger influence in determining this combination. So let me go back. So if I say somehow this here should be the result of bank and river, because I want to contextualize bank here, then well, I can ask the same question. What happens or how important is the word apple when I combine it with bank? And it should not be so important, maybe. Yeah. Depending on the context, maybe. Okay. But what I want to say is here I only have 3 words. But if I have 3,000 words, then I don't want that all the word vectors will influence the new contextualization, but only those that are somehow relevant for bank. Yeah. Okay, so this is also required. Okay, and then this query could also be a word to that embedding. So maybe I have this catalog of 3 words: bank, bank, river, and account in a 2-dimensional space. And maybe I have another word embedding, maybe only 1-dimensional. Every word is just a single number, yeah, but not an integer number, but a real number. And I also have a representation for bank in that space. And then I want to encode bank that was before just 1-dimensional in a 2-dimensional space, but in the contextualized version. Okay. So I will give you another figure, but let's talk a bit about terminology. And I mean, I know that almost everybody here has heard about attention, it has heard about keys, values, and queries, but in my experience, almost nobody understands that really correctly. Yeah. And I hope that with this, you will understand it correctly. Because I think one of the problems is, or one of my problems was that people use too many figures to show the shapes and so on. And it's really a bit distracted. And the important mathematical part is always missing. Okay, so this matrix, this catalog, okay, this is what we will call the values. So the values are, so to say, the context-free representations of the objects. Okay, that are the values. And the Q is called the query. Okay, and again, they are not from the same dimensions. Now, if we want to encode this query Q with this vocabulary, with these values V, then we have 2 problems. Which are the 2 problems?
The dimensionality.
But first is the dimensionality, right? Because I mean, if the query comes from a different dimensionality than the values, I mean, how should I even compare them? Right? Okay, and the second one is, so, okay, basically we already had this dimensionality, and the first one, it's not really clear how we do this. So if we say we have here 3 words, then how do we even test how relevant each of these objects is for the query? I mean, how do we do this?
Only with statistics, maybe? And
it was more like a rhetorical question. Actually, you have no way in this moment how to know this. This is a really big part of this invention of attention. Okay, so I mean, you could do statistical tests, but the problem is that, I mean, how would you do it if the dimensionality is not the same?
Yeah, you have to.
And even if the dimensionality was the same, maybe, I mean, these 2 embeddings of B and Q are completely unrelated. So it could be that bank is somewhere in a completely different region of this space of Q than it is in B. Okay, so even if the dimensions were the same, I mean, doesn't really mean that you can really compare them well. So there's really no way currently how we could do this. So we need some help. Yeah?
But I have one question. Bank in the Google way is a new concept.
Yeah, we don't have it yet.
But maybe I can create a new embedding with this new word. because it's a new concept. It's a new word of the
But
dictionary.
the problem is that it is just one. I mean, yes, this is what we want to do. But the point is that embeddings are right, like in our definition, embeddings are not contextualized by construction. So bank is always bank. And if you don't know what the context is, you cannot embed it somewhere else. So the question will be basically bank plus context, what's the new representation of bank in this context? That's exactly the question we want to solve. So the question is more or less, how do you come from the red one to the purple one? But we are even more general. We say what we come from is not even the red bank in the 2D dimension, but even another representation of the bank. But I have a figure for this. Just give me a second. So,
Yes, just short question. Two short questions. The first one is, when we're talking about the dimension of Q, and we were saying that it is belong to a real space of E K. That K, how is defined?
doesn't matter.
Doesn't matter. Okay. And the second one is that you said that the portion of each word in V should be influenced by its relevance for Q. Like honestly, just to not understand.
Yeah, this is exactly what you cannot understand right now. So you say I have some objects in some b-dimensional space. I have, which are like, which is a sort of my vocabulary I can use to construct the new word. Okay. Then I have a query which I want to represent in this new space. But the query comes from a completely different space. How can it even be possible to compare these and express relevance?
This should be indicating of the linear combination of words to create context. Yes.
Now, let's say you have a two-dimensional so I mean, basically what I'm saying is that it doesn't make sense yet. So, but give me a second. I mean, I have a figure for this, and then I think it will become clearer. I mean, we can already first talk about this. So let's say this is I don't have the account now, but let's say shower. Okay. So bank and shower should maybe not be so related. Okay. Why is it related again with river? Because there is something like a river bank. Okay, this is like the origin of the river. Okay, for those who don't know it. Okay, so here, but again, 3 words. So I have a 3 × 2 value store. This is like my vocabulary in 2 dimensions. Yeah, and the query could be 1-dimensional. Could come from this space, for example. So I mean, how do I even check now? How important is this blue vector here for this point? I mean, even the question doesn't make sense almost. Yeah, but we want this. We want this because somehow here we have something that we want to encode in this space. This is our vocabulary. So somehow we need to find out how important is this guy for the representation of him? How important is this guy of the representation of him? And how important is this guy for the representation of him? Okay. There's no way how we can do this without some additional structure. Okay. And this is what we had on the slide here before. So to do this, what we must somehow do is that every object in this space of V must have another representation, which we call Ki. And that is a representation in this other space, in this 1-dimensional space in my example. Okay, so you say, okay, my river has a representation in the space where I want to construct something. That's where we started from. But in order to make them comparable, the same river object must also have a representation in this other space where my query is being defined. This is where I create the bridge. Here I make them comparable. Okay. So if my river is also a 1-dimensional dot, then I can compare this dot with the bank dot. and I have a bank dot from the other one, I can also compare the bank dots, and I can compare the bank dot with the what? With the shower dot. Okay. So we need somehow another, like a second representation. So like every word in my space V has actually two representations, one in the space where I want to construct and one representation where I want to compare. Good. And next, how do I compare? Well, for this, I will introduce a function. So if I have my space, my query space here, this dk dimension, in my case, the one-dimensional space, then I need just a function that takes two of these objects and gives me a score, or like a similarity score. Okay, and the similarity score will also be a relevance score. Like the more similar or the more relevant, that the more similar the points are, maybe the more relevant they are. Okay, so two things then. Every word in my construction space also has another representation, the query space. And in the query space, I can conduct comparisons through this function. Okay. So if I can do this, then I can ask how relevant is river for bank in one-dimensional space. Yeah.
But I have a question. But this score is not encoding the relevance of B of the vocabulary to the query, right? It's just
No, it's indirect.
indirect.
I mean, in a sense, yes. So what is your vocabulary? River, bank, and shower in a two-dimensional space. But each of them is like linked, connected to another representation in a one-dimensional space. Now, if I say that in this one-dimensional space, the bank is related to bank, well, then that should also be the case in the two-dimensional scenario.
But I don't have a direction for that influence.
It's not an influence. It's not that. It's a correspondence.
Okay.
It's not that some variable influences another one. It's like in causal logic. It's just a correspondence somehow. Or no, it's really more like a statistical
Relation?
Yeah, maybe a correlation, but let's think more like relevance. Okay, and this vector here that I use to describe my word from the construction space in the query space, this is called a key. Okay. So we have now three rows. We have the values, B in the construction space, we have the query from this other space, and the keys are somehow a representation of the words in the value space in my query space to make them comparable. They will be my bridge. So let's look again at the figure. So we have this situation at this point, not comparable. Okay, but now what I say, okay, now in the middle we have the keys. How many keys will we have? Three. One for each word in B. Okay, but how many dimensions will we have for the keys? Three. Exactly. So the key space takes one dimension from the query space, which is basically the dimensionality here, but it also takes one dimension from this one, which says how many words do I have. Okay, so if I want to describe the keys, I need a matrix of which shape.
Or two?
Oh. So how many words do I want to encode? Three. And how many dimensions do I have available?
Two.
No, one. Okay, so now importantly, this coordinate of bank is not the same as this one. It's just really two different spaces. They have now this here, they have the same dimensionality for in this case, yeah, but that doesn't mean that the coordinates of this bank is the same as for this bank. Okay. Okay. But now it's clear that I wanted to draw here, but of course I forgot that I cannot draw on the screen. So what would happen now? So if I now ask how important is the river for this bank, then that would be done as follows. I take this representation here, I take this representation, they are in the same, they come from the same vector space or from the same, have the same dimensionality. So I can put these two guys into the score function. And the score function will tell me a number that says how relevant, how closely related are they. And then I can use this somehow to construct my my neo embedding for this bank here. Okay, so why do I need a new bank again? Because this bank here is the context tree bank. Okay, and that now for this guy here, I have a certain context, and I want to embed it according to this. Okay, so let's see then how we can do this. This is now where the attention mechanism comes into play. So we have a query, which is the point. We have the keys, which is the 3x1 matrix, and we have the values, which is the right figure. So we have these three things, and now we put all of them together into a single function, okay? And that will compute the new representation of bank. And how is it done? Actually, here's what we said on the first slide. We want a linear combination. So we take every word from B, each of the three words, and give it a certain weight. Okay, and then we sum this up. So this here is the jth word, or the encoding of the jth word. Okay, so we go over the three words. Each word will have a weight. Then we multiply the embedding of that raw context-free word with a weight. Yeah. And the question, of course, where does this weight come from? And the weight comes from the similarities. So, well, first of all, the alpha j's will be normalized with a softmax. And that just means that, so we have, let's start maybe here. So we have the similarity scores. So for every word, each of the three words, we have then the score that tells us how relevant is that word for the query, right? So these are just some numbers between minus infinity and infinity. The relevance. And then we take these numbers, and the idea here will be, of course, that the higher this number, the more positive it is, then the more relevant this word number J is for the query. And the lower it is, the more negative it is, the more irrelevant it will be. Okay. So we take these scores, put them into the softmax. What's the effect? That we get a vector that sums up to 1. So we distribute basically 100% of relevance across all the words. Yeah. So I have a query at 100 points, 100% of importance or relevance to distribute across all these words here. And this is what my alpha j will do. So I can think of alpha also as a vector of the same size as the vocabulary v, and it contains for the jth position the portion of importance of that word for a q. Good. So this is a bit confusing because so one big problem of this transformer paper of Vaswani is that they call this here basically the attention, while the attention vector is only the alpha and not the result. So this should actually not be called attention, but attention-based encoding, because this is now the new vector that we want. This is the purple vector. Okay. So, and the purple vector is not the attention. The purple vector is computed using the attention. Saying for each of my words, what's the importance, and then I just sum this up. Okay. So this formula really computes this purple vector from the red one and the blue one. Yeah.
It is that's the objective of the extension function to create new words inside of a vocabulary or just to like locate them into the context.
Yeah, that. It's not like we create new words. I mean, you could even do that. So here we can even, so in my example, the query is somehow the same, okay? The query is somehow the same. This word, bank, also exists here. But in the query, we could also use some completely new word. So, for example, we could use, I don't know, dog, for example, okay? And then you want to embed dog in that space, yeah? So, but it's in general to derive contextualized representations. Okay, good. Now,
But that's inside B, right?
sorry,
That's inside B.
B.
Yes, inside the values. Like in the case of the purple vector, we're trying to like locate this bank as a river, bank as hydrographical feature inside of valley. Is that the case?
No. So we are not making B bigger. We're not creating a new word. It's just like, so we are not, before B had 3 words, and after it also has 3 words. It's only like in this context, B, or in this, if this is my vocabulary, how do I express something in a contextualized way? It's not like we are not growing, we are not adding a word to the vocabulary.
So we're just changing where bank is from the red one to the purple one or to the.
We're not even changing where bank is. We're just saying the bank that is close by a river, that will be the purple one.
Okay.
So the red one stays where it is. It's just if we have some context about the red one, then we want to use this context to create a new position for this contextualized version of the red arrow. Yeah?
Okay, so we're creating like states, you could say, like, so we have like a bank as red, and if we're talking about something related to finance, it's going to become the orange one. And if we're going to talk about something
Yeah.
related to hydrographic, it's going to become the purple one.
Yeah.
Where that information is saved when I'm doing like
It is not saved. It's just, I mean, here we compute it. Okay. So this is the result of a computation. This is just then, I mean, if you do it in PyTorch, there's just a tensor in your memory. You will, yeah, you can compute this and you have a tensor in the memory. You will not store it somewhere else. This is why I say we do not make the vocabulary bigger now because of it. It's just like, it's like we compute this new representation, so to say, on the fly.
okay, so that means that the like it's not like B is becoming like larger and larger and larger. It's not right to have like 10 different types of bank. It's not just farming bank.
I mean, why would we not want to do this? There is just one word bank. And the bank at the river, well, I mean, we don't want to have a word for that. That would be like to invent a new, we don't have a new word for this in our actual vocabulary. So it doesn't make sense to make V bigger. It's just for the contextualization. So in this space of V, you have like let's say the natives, the originals, and they are stored in your memory. Like these you can even have them on the disk. But everything else, which is contextualized with this, is not being stored permanently. It's just like you compute it, you use it, and you discard it.
In this case, bank is the combination of 2 words.
Yeah.
But I can use 4 dimensions.
Yeah, you can use all of the words. But that would be probably not very good. So typically you want only one. If you don't need context, then you just you have a value of alpha equals 1 or close to 1 for the original word, for example. And maybe you will have 2 if there is a context. Maybe you have 3, but much more than 3, 4, 5.
But if I would like to represent a more complex concept, is possible. For example, I don't know. I don't know, a sentence, like a sentence. Maybe it's a concept.
The sentence as a whole could be
And it's a combination of many words, but I want to create a concept that is that just bank.
Yeah.
For example, idioms.
Yeah, I mean, you can use this with anything. I mean, I'm talking about words, but this is really just an example. You could have, so you can have images, you can have optimization problems, you can have, after all, you say, I have a set of objects, and the objects can be sentences, not words. The only thing that you need is that these objects have already been encoded. Because this is what V is. V is already a tensor. So if you have already encoded or embedded at least your objects, you're good. Now, the gag is, of course, I mean, how do you embed complete sentence into? Yeah. So then you probably need to, because for this you somehow already need to analyze the context at word level. Yeah, to make a good embedding of a sentence, you need to analyze the connections of the words at word level. But this is essentially what will happen. So what will happen is that we will encode complete sentences into a single vector, but this will be based on the representations of the different words in the contextualized way. Okay, so this is attention. But here's obviously an open question. Where does the score come from, right? So this is why I said that the attention mechanism is, so to say, parameterized with a score function, which we have not said yet what that is. That will be the second part. Okay. But before we get there, so we now said we just have one query, but actually we have, often we have multiple queries at the same time. Because if we have a sentence, then we want to have a contextual embedding or encoding for each of the words. Okay, so instead of having just one query, we say we have M objects, M queries, and it's like having M of these vectors together. As column vectors, and if we put all of these M queries together, then we just get a query Q or capital Q, okay? And then if we compute these scores for each pair, so for each query inside of this QI, and for each key of my vocabulary, I can compute the similarities. That gives me then a matrix of like similarities. And in this matrix, I can compute the softmax row-wise. So in every row, I apply the softmax. And then I have for every query an attention vector. And I have an attention vector for every query, then I have an attention matrix. Okay, and so here my alpha would not be a vector with n entries, but a matrix m by n. But just generalization. Instead of having one n-dimensional vector, I have m n-dimensional vectors. Okay, one for each query. Okay, good. So, and now we see something interesting. Somehow this mechanism here can really work with any number n. We don't even need to know what n is, because where is the n? N is the number of words I have available in my vocabulary, right? So in my case, it's 3. This 3 is in the size of this guy and this guy. Yeah. Now this is just a function, and here will basically so this sum goes over this dimensionality. J equals 1 and up to n. Maybe I should add this in the slide so that we see here this goes from equals 1 to n. So the attention mechanism can do this for any vocabulary, but it doesn't even need to know in advance how many words there are. So I can, because yeah, this is just a function, and I can invoke it once with I don't know, vocabulary size 3, and later with vocabulary 7. Yeah, doesn't, so it's not like in a fully connected neural network where I need to know the number of neurons, but this is more similar to what? So if we think of this like an operation in a neural network, which is the other operation that is flexible with respect to the input size. The convolutions. Yeah, the convolutions are also agnostic. So here, as long as we have a kind of consistency between the shapes, we can do whatever we want. So what does the attention mechanism get? It gets the queries, yeah, the keys and the values, all of the three. And then it produces a new matrix. So let's analyze these shapes carefully, because this is really can be a bit confusing. So we have queries. The queries are formulated in this dk dimensional subspace. And how many queries do we have? M. So this matrix Q here is M times dk. Okay. Then we have the keys. The keys, we have one key for every word, and we have one value for every word. So these two here are n row matrices. M row matrix, 2 n row matrices. Okay, and this guy is at the same dimensionality of the queries. That was the bridge, and he has the dimensionality of the original vocabulary. And then what I want to produce in the new in the vocabulary space. So this is here my dimensionality. I want to produce new encodings, and how many? Well, one for each query. And I have m queries, so this is here in the shape. Okay. Now this always works. I can always execute and run the attention mechanism for any input matrices. Doesn't matter as long as they are consistent. So if I need that these two have the same number of rows, I need that these two have the same number of columns, and I need that this is this number of rows from here and the number of columns from here. And as long as this is satisfied, I can have any configuration here, no problem. Okay. Actually, there is no such thing like neurons or so in the attention mechanism. It's just a function. Just a function. And the formula for the function was on the last slide. So, yeah, so here we have what Nico said. So this is comparable to a convolutional kernel. It's the only operation that I know that works like this, that is somehow agnostic, except maybe like recurrent networks, which we start seeing next week. Yeah. But they are very different because the convolutions have like this local concentration. Yeah. So I have a pixel, and I look what happens around this pixel. This is what a convolution does, for example. Or I have this time series, and I look what happens around this point of time t. And attention doesn't work like this. Attention just looks at everything simultaneously. Yeah. Because I look at everything that happens in my area of perception, and this area is a bit defined here with these guys. Okay. Now, what I said up to now, attention is just a differentiable layer for lookups. I mean, what's the difference between an attention right now and an embedding layer? Well, an embedding layer takes an integer or a natural number, says, that's my index for the word, and I give you a vector. So I could think in an embedding layer of this index like a query, but just an integer query, and I get my vector in the B space. So that's similar, but that is context free. Yeah. Now, attention allows me somehow to mix different words in the target space. So I'm making embeddings more flexible. So when I come with the word bank to the embedding layer, well, he gives me exactly one representation. That's like a bit extreme. So it's like it puts weight 1 to one of these vectors in the lookup table, and the rest has weight 0. So what we're basically doing is we have this embedding matrix B, and instead of picking one row from this matrix, we combine some of these rows. Okay, so one way to think of the attention mechanism is we're making a kind of soft embedding, where the new word, the word embedding or the object embedding, is a linear combination of some of these words from B, and not just one of them like hard. Okay, but in the embedding layer, I learned something. I learned the embedding matrix, but here I don't learn anything. I just have a function that does the mapping. So where is the learning? And until after this point, there is no learning. Just we say we have something here, we can compare things, and then we can output something, but nothing has been learned so far. Hopefully you have learned something already, but the framework, we have no learning yet. So this is a bit worrying, yeah, because who says now that, I mean, okay, so maybe we have a reasonable function to compute similarities, yeah? But who says that the key for a bank is somehow similar to the query of bank? Yeah? So how can I detect that? I mean, how would you do this? How would you here detect whether this bank is similar to this bank? Well, obviously, somehow through the notion of distances, yeah. So where is this bank located? Where is this bank located? And then see, okay, how far away are they from each other, for example? Huh? Somehow you can try to find out how similar they are in this space. And similarity would always somehow define in terms of, there are different similarity metrics. Yeah, we already know kernel theory, so we know RDF kernels, we know distances, we know dot products, for example, so cosine similarities. But what if, like, this encoding here is like at -10, and this here is at +3? But then any similarity function will tell us they are not related. Okay. So here they are more or less closely together. So this is, let's say this is at position 1, then this is 1.5. It's not so far away. Okay. But if this is at -10, then I will not be able to predict, at least not based on distances, that they are still related. Okay. So this is one problem. And this is what I mean here with they speak different languages. Okay. So the fact that the keys and the queries are in the same dimensionality does not mean that things that should be closely together actually are closely together. Yeah? The other thing is that that is what I said on the first slide. What if I want this additive idea? I want that I can add up some vectors, and that gives me meaningful semantics. But maybe the way how B is constructed doesn't allow to do that. And I will always keep mixing up things when I try to linearly combine concepts, because the positions of the original words in B are bad somehow, and they don't allow for good combinations. Or if I try to combine them, I always get overlaps. Yeah, and then suddenly I get the same representation for a bank by the river and for a fly on an apple for some reason. Okay. So maybe this embedding B is not so good yet to do this. So there is something I want to learn.
That's right. That means that it's possible to have like two words that are not related, really close inside B.
So suppose that we have bank and river, and then maybe the combination comes here, okay? And now let's say that you have apple is here and fly is here. And then if you want them to have them together, they will also be here. Okay? So it could be that the embedding B in itself is okay, yeah, and allows for a good separation inside of that. But if you want to apply this logic of combining vectors, then maybe things start to mess up. Yeah? So maybe this word embedding I learned with word2vec is not very useful for at least because it doesn't have this additivity, this composability property.
Yeah, in the next, when I have one dimension, the graph, why I want to know what is the relation between the original bank and the new bank. Why I need to know this relation, because the original bank actually doesn't have a real meaning, right?
And maybe in that context it has.
Yes.
So, I mean, you can say here in this figure, you can say, I have 3 word2vec embeddings. 2 one-dimensional embeddings that have been trained differently somehow, and 1 two-dimensional embedding. So I would say all of them have a meaning. It's not like they don't have a meaning. So here I will have other words.
Sorry, but it's incomplete, because only bank can have a meaning. It depends on the context. But the only word bank is, yes, we have 50% of chance of is that real.
Well, the word bank has, first of all, it has a meaning for itself. You know, when I say the word bank, you will think of something.
But maybe I think different than other person.
Yeah.
Depends on the context.
Yeah, but I mean here, so would you say here that bank has a meaning here or not?
Yes, this bank, yes.
Yeah.
But the original one, no.
Why not? I mean, where does this here come from? Because I trained a word2vec embedding, like we did on sheet 2. In a tech body of text. Okay, so you did that.
That's my point. It's already had some kind of context from the
Yes, but wait, we're still in the initial phase. So wait, we get it. But so when you say when you admit that this has sense because you train a word2vec embedding, for example, yeah, then this can also have sense because you can also train with a word2vec embedding of dimensionality 1. And here you also train a word2vec embedding of dimensionality 1, but maybe with a different text corpus or so. So for me, it's not reasonable to say that this has meaning, but this not. What I think the question behind the question is, yeah, okay, but how did I really come up with these embeddings? And that is a really good question, but this is like what we will see in a bit. Actually, on the next slide. Oh. Okay. So the question is now, so what we have seen so far is suppose that you have these 3 embeddings of queries, keys, and values, then we can compute similarities and create like contextualized embeddings. But the question is now, we have not used data at all up to this point, except maybe to pre-train these embeddings. Yeah. The question is now, how could we use data to improve this matchmaking between the queries and the keys? Because currently it could happen that these 2 spaces don't fit. Yeah, they are both one-dimensional, but since the embeddings have been trained in a completely different way, there's no way how I can find out that the query bank is the same or closely related to the key bank. Yeah, so I must allow them. What I want to make sure is that I can somehow make these representations similar so that similarity measure has a chance to detect that they are the same. Okay, so this is the first. We need data to make sure that representation of bank as a query and representation of bank as a key will be similar enough so that the similarity function will fire. And if they are not similar, then the similarity function should not fire. So that's the first thing what we would want to like to use the data for. And the second thing is that we want to use the data to make these vectors in B. We want to configure these embeddings in the space B in such a way that we have this nice additivity property. Okay. So this is what we want to use data for. And now we could say, okay, wait, these matrices Q, P, K, and V. So queries, keys, and values. These matrices that we use in the attention mechanism actually are not pre-trained embeddings, but they have before been passed through something that we can learn. Okay, so what we say is that actually the word to vec embeddings are here, Q0, K0, and V0. That comes from something before we don't have under control, but now we take these, like the basic bang embedding, and we process it with some modularized module. Could be some small neural network, for example. Okay, but in this neural network, we have weights under our control that we can learn. Okay, so if we can say that, okay, we have some initial representation of all of these things that we cannot influence maybe, but then what we just say is that we put a step in between. We take these raw representations and derive useful representations for us. And to make them useful, we put a mini neural network in between that can learn parameters. Okay? So this is like this small additional step. And this is what we call an attention layer. So the attention layer, the attention mechanism has nothing to learn. It's just a function. It's like an activation function almost, okay? So think of the attention mechanism as an activation function. But the attention layer now says, okay, I get these raw inputs, which are not under my control. And with these raw inputs, something can be wrong. Can be that there is no way to see that bang is similar to in the query and in the key. But I want them to be similar. What's my way to do it? Well, I put my mini neural network here, okay, and from that, for each of them, I have 3 mini neural networks, one for queries, one for keys, one for values. And each of them can learn something. And what I want to achieve is that bang here and bang here are closely together, so that the similarity function can fire, even if they were not closely together here. Right? And what I want for V is that I get this additivity assumption, that things are like concepts can be nicely added for contextualization. Okay, so my embedding layer, my attention layer would first apply these 3 mini neural networks to get better representations of queries, keys, and values. And since this thing has the weights it can learn, well, we can improve upon that, okay, with data. And then I take these improved ones, these here, and then I put them into the attention mechanism. Yeah. So this is what an attention layer does. And this is mostly the homework exercise. Okay, so you will, this is of course implemented in PyTorch, but you will implement your own attention layer from scratch, because it's really important to understand how this works. And you cannot understand this really well if you just use the library. And it's actually very simple. So this guy then has a slightly different shape. So this here is the same thing, except that now we have these funny zeros. And actually up to this point, I haven't talked about the zeros. So when I say that here I have this Q0, K0, V0, so these are like original representations, like my word to vec embedding, but these come from other dimensionalities. Okay, so this comes from a DQ0 dimensionality. So this could be my 1. Okay, so this could be my 1 dimensional. This could also be 1 dimensional, but the funny thing now is that in this original space, these do not necessarily have to be the same. So maybe now my original query is 1 dimensional. My original key is 3 dimensional, and my original value is 2 dimensional. Yeah? Or even 70 dimensional, doesn't matter. Since I now have a network in between, I can make sure that internally the queries are mapped to the same dimension as the keys, no matter which dimension they had before. Okay, and I can make sure that the values will be the size, no matter what they were before. Okay. So attention layer is translation plus attention. Translation means I change the original, I modify the original representations using weights that I can learn. And this is the important part. Without that, I couldn't do anything. But this allows me to put things together that should belong together. Okay, so how could these mini neural networks look like? Yes, these mini neural networks to transform Q0 into Q, K0 into K, and B0 into B. Well, in the simplest case, that would be just a simple linear network with a single layer, right? And this is actually what is being done. So in the simplest case, we would say that this transformation we do just with a single linear operation and even without bias. So what we would have then would be this. We would say this query matrix we obtain by taking the original query matrix and multiply it with some linear weights. Okay. So this guy here is our linear transformation to map, create a linear projection from the original queries into the queries where I want to do the comparison with the keys. And for the keys, I do the same thing. I take the original keys and I map them with a linear projection into the space. Now, these two, maybe Q0 and K0 are not comparable. So maybe bang in Q0 is here and bang in K0 is here. No chance to identify them. But since I do this mapping in these two spaces, then, or in these two metrics, bang could be closely together. And that is precisely the job of the network, to learn a good W where that will be the case. Yeah? And for values, I do the same. So I have three mini networks, which are basically nothing else than weight matrices. So linear layout, even without a bias. You can use a bias, but it's not relevant. You don't need it. Okay, so the optimizer can now learn good weights for this, and that will allow us to actually create meaningful contextualized embeddings. And with this restriction here, it is called a linear attention layer. But this is so common that in PyTorch, there isn't even another one implemented. This is the only one that exists. In principle, you could do more complicated things here, but it turns out that it's not necessary. So, no, we don't even have an activation function. It's just a linear projection. Okay. Now, here's an important difference to the attention mechanism. So the attention mechanism is completely agnostic to the dimensionalities. I can just input anything. I don't need to configure anything before. But this is now different, because if I have the attention layer, in the attention layer, I now have these weight matrices. And these weight matrices, well, I need to initialize them at the beginning, and they need to have some dimensionality. So if I want to use this, then I need to know at least what's the original input dimension and what's the dimensionality in which I want to do the comparisons. Yeah? So here I have DQ0, DK0 are the original dimensionalities for queries and keys, but I want to compare them in some dimensionality here. This is basically a hyperparameter of the layer. I can say, what is the dimensionality in which you want to do the comparisons? Do you want to compare in one dimension? Then this will be a 1. Do you want to compare in 10 dimensions? Then it will be a 10. Okay. So this is a hyperparameter. This here depends on my input data. And this is, this can also be a hyperparameter. Okay. Okay, that was easy. Now let's talk about these score functions, because up to now we have not really said how do we compute similarities. So what I really find interesting is that people think that Vaswani introduced attention, and that is just a lie. Okay, so I mean the paper is over 100,000 citations, but they did not invent attention. Actually, they were not even the second. Okay, so the first one who came up with this was was Benjo with one of his PhD students in 2014. But first, let's check what are our expectations for this function. So if we have a single query and a single key, bank, query, bank, key, what do we want? So we have the embeddings. We have the embedding of bank as a query and the embedding of bank as a key. So what do we want now from score? How should score behave? Similar. So remember, how is the score later being used in a softmax? Okay, so actually score produces a logic. So if they are semantically similar, then score should produce what? High positive value. And if they are very dissimilar, then score should produce a very negative value. Okay, so so the idea would now be that we can so either we just come up with a non-parametric function that will just somehow take these two representations and compute a number, or we inside of score we also use a parameter somehow to control this behavior. What's this? So here, okay, so that was the first one that was presented by Balan, so 3 years before the Vaswani paper. And what they did was to say, okay, we compute similarity like this. We take these two representations, the query and the key, and we add them. Oh, that looks funny. Why would we do this? Okay, and then we take these two are vectors, right? They are not numbers. These are vectors. So we add two vectors, and then we compute the tan h at each position in the vector. Tan h gives me a mapping between -1 and 1. Tan h always produces number, so it's closely related to the logistic function. Actually, you can see there is a close mathematical connection between the two. So here I get a vector with values between -1 and 1, and then I compute a dot product of some weights. These are like internal weights of this function that can be somehow learned. I show dot product of these weights with these tan h outcome. So it's a bit like an activation function, yeah. And this here is important because it introduces non-linearity. Because here it's linear. If I would just multiply with this, that would be still linear, but the tan h introduces non-linearity. Now, why do I add these two? I mean, why should I say that somehow presents similarity? The point is that we don't really need yet that this here by construction will naturally will be a similarity, because we have a parameter here. So we can just say, so here the interpretation is like this. Q plus K really doesn't have specific meaning. It just says a Q plus K is the way how I represent this pair. Yeah. So Q has a representation, K has a representation. What is the representation of the pair, QK? And they said, well, I represent this through the sum of the two. Yeah.
Like it shouldn't be like the figures, for example.
Yeah. Right. You could also concatenate them or so. So there is really no specific meaning for this. It's just saying I want to represent the pair as such. Okay, so there is no more logic like this. Then this has the motivation of introducing nonlinearity, and the job of this guy is precisely to make sure that we can learn something like similarity, because here there is no similarity. It's just like putting things together to have a joint representation. So this W here needs to be learned so that this really will represent that. So this W must make sure that if things should be similar, that we will have a high value. If they should be dissimilar, that we have a high negative value. That will be then the job of the W. Okay. Okay. Perfect. Now, this paper, and by the way, the slides have these papers now on the last slide, so that we can see where it was presented. And I really recommend everybody who wants to work with attention to read these papers. So this was also super influential paper and a huge milestone for this whole area, because basically they started with this idea of attention at all. Okay, good. So, but then 1 year later, people came up and said, okay, but I mean, why do we learn a weight vector when we already have ideas of how to determine similarity? Because usually the dot product is used to express similarity, right? Because it's related to the cosine of the angle of the vectors. And this is why then Luong and 1 year later introduced the dot product attention, where you say, you know what, let's make it simpler. We just say the similarity of Q and K is expressed as the dot product between the two. Right? No parameters need to be learned. That's all. Okay. Now, in their paper, they actually didn't do it exactly that way. They also learned a weight matrix here in the middle, and this is because of the following. So when we have this, representation, and we say that before we encoded the queries and the keys with our linear layer, like then this Q is equal to applying to the original query Q0, this linear transformation, right? And the same for the key. Now, here I have a transposition of something. So if I put the transposition into the bracket, then I have Q0 transpose WQ transpose, and they flip sides. Okay, so what you get here actually is this. But then in the middle, you have a matrix multiplication. So I have this matrix times this matrix. And then I could say, oh, then this is actually a bit expensive. Why don't I just have one matrix here? That is already the result. So I learn maybe these, I learn this intermediate matrix directly. So what they did in the paper was they didn't have this network before. Yeah, they didn't say I have the Q0 and the K0 and I first encode them, but they said, and what is encoded already comes in, but they say I take the original values and then compute this operation. Then I have only one matrix multiplication. Yeah, and I also only learn the weights for one matrix and not for two matrices. Yeah, not for this matrix and for this matrix. Okay, so they did that, but later, then Vaswani again said, okay, yeah, you can do it, but the point is these two matrices are smaller than this one. So somehow it's more efficient, or it turns out that it's more efficient to learn weights in two smaller matrices and do two multiplications instead of learning one big one, okay? Yeah. Okay, so then in 2017, Blix and Al, they did a very interesting comparison, because one could ask, okay, which of the two is better, additive attention or dot product attention? So, so they compared the two, and what you see here is, so they had a single task, a single translation data set. Yeah, I think it was English to German. And they said, okay, so what's my blue score? This is basically a number that is measuring how well the translation works. Maybe at some point we will talk a bit more about this, but not today. So the more the better, okay? Higher means better. So what do we see here for the dot, so mul means multiplication. Okay, so this is the dot product attention. And what this means is decay. What is decay? Decay is this dimensionality in which I want then to compare queries and keys. Okay, so they don't use one, as in my example, but 128. It's a bit difficult to visualize. But so comparison 128, 256, 512, or 1024 dimensions. Rather high dimensional space, yeah, to compare keys and queries. And what we see here is that the blurry score really, so first of all, the model, of course, becomes more complex, right? So they have here models with 65 to 67 million parameters. And what we see is that the performance decreases. So the fact that we just use more or a higher dimensionality for the comparison makes that the results get worse. Now one could say, okay, but this is a general problem. If I have more parameters, then maybe I start overfitting or so. But when one looks at the additive attention, one sees that this effect does not happen. So here the results are roughly the same. And I mean, yeah, here it's a bit less than this, but this is all still in the standard deviation. So this is, it seems then that additive attention is more stable with respect to the dimensionality size of my, where I do my comparisons, than the dot product attention. Right? And I mean, they observed just that, but that was more like a result of their study. It was not like their motivation to do something. But then now, yes, Vaswani took this, picked up this result and made an interesting observation. So assume that you pick a random query and a random key. So we have two random variables, and then you compute the dot product. That will be just a number. But since the key is a random variable and the query and the key both are random variables, then the dot product is also a random variable, right? And then the random variable has a variance. So what's the variance of this random variable here? And this is the output of the similarity. So basically, we're expressing the variance of the similarity measure. And we would like that this variance is somehow limited. But what happens? So this dot product, well, what's the dot product? The dot product is the sum over all the products of the entries, right? Oh, that didn't go as I want. Okay, doesn't matter. So this is the definition of the dot product. Go to the entries and multiply each of them together, okay? Now, if I assume that these are IID, then I can take the sum out. Because if I have a sum, if the variance of a sum of random variables is the sum of the variances of these random variables, at least if these random variables are independent. Okay? They don't even need to be IID, only independent. Okay, so I can then do this. If I now also assume that they have the same distributions, then I can say, well, let's say that this is just a constant variance, sigma squared. Okay. But then I'm just summing dk times, like my dimensionality times the variance. So what we see is that the variance here of this similarity measure directly increases with the dimensionality. And this is an explanation for this instability. Why? Where do my similarities go to? I compute the similarities, and where do they go then? Where do I put the similarities?
Should I have attention?
Before, in the attention. So I compute the similarities. These are logits, and the logits go where? Into the softmax. Okay. And now what happens if I have a very high variance? Here, what does that mean? High variance means that some of the values are super large and some of the values are super small or very negative. Okay. And that means that I get very extreme scores that I put into the softmax. Yeah? It's not a problem if the values are high. If they are in the millions, that's not a problem, because as we saw in deep learning, the first course, you always translate this with you transpose the inputs of the softmax. But if you have both very high positive values and very high negative values, then you cannot do that anymore, and then you will really have an explosion, and you will basically get gradients that are close to zero. Because if you remember the sigmoid, the logistic function, the logistic function goes like this. And what happens is, I mean, the gradient is always different from zero, but it's very close to zero here and here also. And if we have very high or very positive or very negative values like here, then so if this is my score here, then I have a gradient that is almost zero. And if I value that is here, then I have also a gradient that is almost zero. Okay, so that means that high variance in the scores is a bad thing, because that introduces a problem for learning. So what this theory here, it's not a theory, it's just like, and you write that in 5 minutes. But what this here says is that in this dot product attention mechanism, you buy yourself problems if you use large dimensions. Because if you have a high dimensionality, then you will automatically buy in vanishing gradients. And then it was very logical to say, yeah, okay, but if this is so, then why don't we just normalize this? So I want that here on the right-hand side, I have a constant like sigma squared. So what could I do? So I now want something here where I use the dot product, and I want that the variance of this will be sigma squared. So what do we need to do?
Divide between
Okay. Almost. Because by the square root. Why? Because this is a constant, and if you have a variance, you can take the square of a constant and take it out. So this is equal to 1 over dk times the variance of qk k. And this here is then times dk sigma. Right? These cancel out and you have sigma squared. So there's really no big deal about this, but this is exactly what they did there in the transformer paper. But I also want to be clear. So this is not a game changer. Okay, so this is important. This is important for learning success, but this is not why transformers are so successful. This is only part of that story. Okay. And last one. So those of you who saw several courses with me already know that I always say, yeah, okay. So the dot product is somehow the cosine similarity, but it's not exactly. Okay? It's not the cosine. So the dot product between A and B is the norm of A times the norm of B times the cosine of the angle between A and B. So if I want, so the problem here is that this is not between 1 and -1, and maybe I really only want the direction. If I have the cosine, then I know the direction. So I can basically take, but then this is the same as to say, I can divide by this. Okay, and then I get the cosine of the angle between A and B. And this is what they do. So the cosine similarity takes the dot product and divides by the norm of the vectors, and then I get a value between -1 and 1, which is the angle between Q and K, and the cosine of that angle. And if the angle is 0, then I get a 1, because the cosine of 0 is 1, and this is nice because they have a high value for similarity. If they are unrelated, then I have a cosine of pi half. Okay, so that would be a value of 0 for list. The same is for 3/4. And if they are opposed, then I have the cosine of pi, which is -1. So that would be like an anti-similarity. Okay? And this is also nice because then I have similarities that are between -1 and 1, and they are in a moderate space here. And I don't get these exploding gradients. Vanishing gradients. So, okay. Very good. Then basically, if you understood it up to here, you have it. Okay, so that's the important part. There are some slides left to explain self-attention and multi-head attention, but this is really now simple. Because it only says how should we now use this in a specific case. Okay, so now let's say, because still the question is a bit, okay, but where do these queries come from and keys and values? So, okay, so now, and this is one of the important contributions of the transformer paper. So we now say, let's say we have an instance, and the instance is a sequence of arbitrary lengths. Yeah. So N is the sequence length, and D is the representation space. Yeah. Okay, so we have a sequence of pixels, sequence of tokens, and we have just assumed here that we flattened already. Okay, so if you, so D means that we flattened already. If you have images, then you flatten the image. If you have a time series with several variables, you are flattened. Okay, so we don't need an extension for tensors. Yeah, with matrices, it's okay. We will always say that we don't, and this is because the attention mechanism doesn't have this local spatial processing like convolutions. Okay, so we can always flatten if we have something higher dimensional, and then we have an instance that is basically a sequence of D features or D sequences of length n. Okay. And usually, you know that I write instances with lowercase x, but here, since it's a matrix, I will write it in capital notation. And now the idea will be, okay, so we have a sentence, maybe let's call X a sentence because it's a sequence of objects. And even if it's something else, so let's say X is a sentence, what we want is we want now to create a new representation of this sentence. And each word in the sentence should be represented based on its context in the sentence. Right? So now we are back to the bank example. And this is where now self-attention comes into play. Self-attention just means that Q, K, and V all are linear projections of X. That means that Q0, K0, and V0 are all X. So I use the same original representation for all three of the things. It looks a bit weird, but what actually happens is that we define different roles, okay? So we say, okay, I have a word. Okay, so formally it would be that, right? So we said our linear attention layer takes the original queries, this is Q0, and multiplies it with this. Here we have K0, and here we have V0, okay?
That's not similar to iterative autoencoding. Sorry, to iterative encoding.
You mean autoregressive?
Yes, sorry.
No. This is really not related because here, or maybe there is some link that I don't know right now. But here it's just let's better think of this in the form of rows. Okay, so so we have just one input, which is a sentence. But now we create three different versions of this sentence for different rows. V says here we define the space in which generally we want to encode the words. So here we define the base vocabulary in the new space that is available for these words. Here we say for each word, how should I write this or represent this word if I want to check similarity? And here I define, okay, these are the words I want to embed in this representation. Okay, so the query QI now says my word number I, how should I represent it? Yeah, in this context. Or not, sorry, not in this context. How should I write the query? The key says for each word, okay, if you want to be my husband, so here we have the boyfriend, here we have the girlfriend. So here we employ the boyfriend, here the girlfriend, and we want to make a good match, right? So for the same word, we also have, but so for one word, we say, how do I want to be queried? So if I'm the boyfriend, then how do I look like? If I'm the girlfriend, then how do I look like? Yeah, for the same word. And finally, what is my representation in the final space where I want to create these campaigns? So the purpose of these two is to make sure that I put together what belongs together. Yeah, that representations here are closely related if there is a semantic similarity. They don't know what semantic similarity is. That needs to be learned in this W matrices. Okay, and here I want to learn. Here I want to learn a useful representation for the downstream task. This is why these two are in red, because here I learned so that these two belong together, and here I learned that I can do something useful with that later. Okay. All right. Okay, I should take this out. So if we do this, this is a really not so good figure, but it was the only one I found so far, and I will replace that at some point. But it's just saying if I have self-attention, then the attention matrix is alpha, right? The alpha in the attention becomes. If I have a self-attention, then I have my attention matrix is a squared matrix, where the ith row has the same meaning as the ith column, only that this is queries, this is keys. Okay. Now, what is not so nice here is actually these values should sum up to 1 for each column. Sorry, for each row. Okay. Which they don't do here. I don't know. This is I took this just from a website. It's a crap site, but at least it serves as a kind of example. So what I typically would expect in the attention matrix is that I have high values on the diagonal, because usually in self-attention, okay? Because typically the word that is most important for me is itself. Yeah, is itself. Yeah, a word is usually always the most important to itself. But then there are other words that could be important. So here we see that father is really only important for itself. Now there's no mass on the others. But then wanted also has high mass with 2, and it makes sense. Because wanted and 2, this grammatically should be somehow related. Yeah? And here then with 2, we have a high connection also with nothing and do. Nothing to do makes sense. Nothing to do makes sense that these 3 are somehow related. Okay, so we see that we have relatively high values for all 3 here. And here we can then see how this contextualization is created. Okay, so these are the alphas, and then we see, okay, if I want to have the new embedding for 2, if I want to have the new embedding for 2, then I need like a linear combination of these 3. Okay, this is then my new presentation. So, new example. Look at this sentence. After she withdrew some money from her account downtown, she sat down by the bank of the river to watch the skyline. Now, which bank is meant here? Well, we of course know that the bank should be which one? The river bank. But in the same sentence, we also have the account. And what will happen now is, what will happen now? So what's M now? M and N in a self-attention case is the same, because the number of query, I have one query for every word, because for every word I want an embedding. I also have one value for every N. I have one B value for every word. Okay, so M equals N in this case. So what will happen? The bank will attend to both. Okay, because I have a similarity with river and I have a similarity with account. So I will somehow assign some alpha value to bank itself, some alpha value to river, and some alpha value to river and to account. Okay, and what will happen? So this is the original situation, and what will happen? He gets some alpha, he gets some alpha, and he gets some alpha, and the other words get alpha almost zero. Okay, so what will happen? So he gets 1/3, he gets 2/3, and he gets some portion, and he gets 1/3, and then I'm somehow in the middle, which is not really what I wanted. When I wanted the river bank should be here, but it is not now. And if I learn that river bank is here in my downstream task, then I will not detect this here. So here we have a problem. Okay. So somehow it seems that attention is not enough, or maybe yes, it is. So the idea here is then to use multi-head attention, and that just means that you do not just learn one attention block, one attention layer with one WQ, one WK, one WV, but you do this 2 times. And if you have 2 different guys, then one can learn how to embed bank in the context of river, and the other in the context of an account. Okay, and then you don't have this problem. So this is also what Vaswani introduced in their paper. So they say I have not one attention mechanism or one attention head. They call it an attention head. Basically, I have like different possible mappings here. So head I is just the attention mechanism for one of these matrices I. Okay, so this is why it's the super index. And what they just do is that I say I have H of these. I have H mechanisms, and at the end I concatenate all of them and I put them into a linear layer again. Multi-head attention is just nothing else than multiple attentions that are then concatenated and mapped into a single representation finally. So you can think of these heads like specialists. You have a team. Instead of having just one attention mechanism for a good embedding, you have different experts that are specialized in different things. So think of multi-head attention as specialists, and all of them get the same sentence, but one checks for grammar, one checks for modifiers like negations, for example. Yeah? Because negation, that used to be a big problem. I don't like blah, blah, blah. So understand the difference between I like and I don't like movies, because like movies is in both, but understanding that there is a negation, this is what meant by modifiers, okay? And then you have pronouns. The bank, which, so which, what does which refer to in the sentence? Okay, then maybe you have a specialist for that. Now, you do not say you're a specialist for this, you're a specialist for this. this is the amazing thing. If you just have enough data, well, they would specialize in something you don't know what they specialize in, but it will somehow work. So here, example.
Some way there are like the kernels in convolution that you test a lot of kernels to find. Sure.
Yeah, I mean, the point is that kernels in neural networks are somehow inherently a bit incompatible because kernels do an implicit feature mapping, and neural networks always do an explicit feature mapping. But in a sense, you're right that the functionality is a bit similar. Yeah, but the difference is that in the support vector machine, you define the kernel. You say which kernel you want to use, and here he just learns with representation automatically. So support vector machines or kernel-based methods do not learn better.
We don't specify, but we just said in the convolution use.
Sorry, you said convolutions. I thought that you said no, right. You mean the convolutional kernel, not the support vector machine kernel. Yeah, exactly. Yeah, okay, then you're right. So this is exactly the analogy. But not the kernels like the channels, like the filters. No.
So they're not the matrix that you multiply for.
Yeah. So in a convolutional network, you want to have a certain number of output layers from the like output representation feature maps. And this is what you define in the number of filters or the number of channels. And then, yeah, exactly. So that would be the analogy. Yeah. So number of channels or filters defines then the kernels. But the point is that you also have several, in convolutions, you also have several kernels for the input. Not only for, you can only have one output channel, but still you have several kernels because you have several input channels, right? But yes. So the number of of attention heads here, that would be basically the same as the number of filters in a convolutional network. Yeah? And here you could have, for example, one head that is specialized in the connection between adjectives of nouns. So I have a car, I want to see what's the color. And then I have one attention head that is specialized in finding out that.
But it depends on the language.
Yeah, of course. That's all super specific for, I mean, he doesn't, this depends, what is your training data? So you put in training data and he will learn to do good representations for that. Now, what they did for these modern architectures is not that they created networks that somehow miraculously understand all the languages. They just put in data sets of all languages. And you have another head that understands what the subject does. So you have one head that says, the car is red. You have another head that says, the car is moving. And these are, so to say, your features. Like in the convolutional, like say in the convolutional network, your channels are the high-level features. And this is the same for attention. Yeah, so it's kind of high-level vector-valued features.
There is attention mechanism. You don't have words, you have tokens, and tokens are just flags of some kind.
Yeah, I mean,
So just to clarify that, maybe we are thinking in languages or words, but it's not the way that the model works.
exactly.
But, for example, in English, the adjective is before the noun, but in Spanish is first the noun.
But
But the thing is that in this kind of models, you basically use, because, I mean, if you have Chinese, you have kanjis. Those are not words that brings and whole meaning. So basically you split every symbol or in bytes,
Yeah, exactly.
in bits.
So I mean, if you let's translate, what does it mean if you also want to do Spanish? What would that mean? It wouldn't mean that in the first place, it would mean that you have to make your dictionary bigger. So you have more possible tokens. Yeah, and your embedding layer for the symbols is bigger because now you have English words and Spanish words. And then this guy only learns, okay, if my embedding comes from the Spanish language, I will have a different attention head for that. And if my embedding comes from the English language, I use an embedding head for that. So it's just what Rolf said. In the end, it really doesn't matter. You just need enough data, like your vocabulary size needs to be large enough for what you want to do. And if you want to cover 20 languages, you need enough tokens, like indices for all of that. And once you have that, then you need enough data to automatically adjust this whole machinery here. Okay, very good. So you have now understood attention, or at least you heard. Let's check next week in the
We have one head for attention. So now we have two.
Yeah, now you have homework to do. Yeah, okay, but I think it's going to be again pretty simple, maybe not as simple as the last one because that was almost an insult already. But yeah, I think it shouldn't take you longer.
It is better to see it in this way with all the transformer figures and drawings about
Yeah, I think this is a big problem because these, like, there is a very nice blog. I cannot also share it with you of someone who really has a very detailed explanation of the transformer paper. But the problem is that understanding attention is independent of transformers and is not so simple. It's not so trivial. So that should be really taken apart. And then once one understands that, then understanding transformers still has its challenges. This is why there is a dedicated class on transformers as well, but it's not so difficult anymore. And yeah, so of course, here was a lot of text, but the idea is, of course, that you have this text also. Like, these are not like nice slides to present only an idea. This is like to give you also material so that you can really look at everything in detail, understand in detail, implement from zero, and then you hopefully get really the idea of how this is. Okay, great. Yeah, nice weekend for everyone.
Thank you.
Thank you.